So I'm planning to go through every single experiment in the Hodgson Lightbook manual, and the first one here is just reflection of a single ray. So we're just trying to get you to do a proper ray diagram here and label everything correctly. So I'm just following what it says there. So I'm just putting mirror, so you can see the mirror there. There's a front face and a back face, and the reflection comes off the back face. But when the ray hits the mirror, it can also have a little bit of a little bit of reflection, a small amount, but most of it should come from the back of the mirror. So you just put little dots at the front and end of a line, so you can get a ruler and draw it in. And so I'm just marking out where the mirror is. I'll get a ruler in a second and mark those out. And I draw little dots just about in the center of where those lines are. And then I'll measure all those out. So just grabbing the ruler. So it's sort of important that you use a ruler and a protractor for all of these. And in an exam, you'd have to use a ruler all the time as well. So I sort of guessed how thick the mirror was. I think I went a bit too thick on that. So I'll zoom in on this so you can see what I'm writing. Now that you can see the general setup. And then I just draw a line which will be the reflected ray. I really should have drawn an eye. The reflected ray goes into your eye. Now, there's a lot of reasons for that. That one's the incident ray because your brain will interpret everything as a straight line, and it's sort of a link to remember the biological part of all of this. And the colors, I'll get into a lot of depth in the colors, why it's important to realize the cones in your eyes and the filters and stuff. And then for the imaging at the very end, you need your eye as well. And basically, most of it won't make sense if you don't realize it's going into your eye. So we technically shouldn't be seeing any of those lines right now, but there is some scattering. So there's a bit of light scattering off the paper, so I can see where the lines are. And they even make those lenses and so forth. They put a coating on the bottom so that it shows and you can see where the lines are as they go through the lenses. You technically shouldn't be able to see them, as you saw in the first video on something that's transparent. So the most important thing here, and the most thing people get wrong, is to draw a perpendicular line. And the manual says for curved mirrors and stuff, you're not going to go where the straight, it's not going to be a straight mirror. The easiest way is to do a normal. So you always got to draw a line perpendicular at 90 degrees to where it hits. Always label them. So I'm labeling the incident ray there, and I do an arrow in the direction it's flowing. And then I'll do an arrow for the reflected ray. So the arrow going out really should go into an eye and reflected ray. So if you don't, make sure you always do the arrows. And I'm going to also label theta for the angle. So theta for incident ray and theta for reflected ray. And so that's how you never do those out. Those are the ones that students stuff up in exams. That's not the angle, okay? You have to draw an imaginary normal line. Now, I'm a little bit surprised they asked explain the second theta reflected ray because we're not at that stage yet, but you can at least see what's coming up and why it's important to do all the things that we're about to study. So first of all, just seeing that you can just see that everyone else has the same issue, that it gets more faint and it spreads out. So you can see it's quite bright here and then it gets quite faint over here. And then this second one here, you can also see that it's very bright at the start, then it gets faint and it spreads out. And so I've drawn a ray diagram here to explain that. So the source is quite a large lamp inside, and what's going on is that not all the rays are parallel. The ones on this at the top will have the greatest angle down here, and the ones down the bottom will have the greatest angle out here. So as the ray gets further and further along, it spreads out. You can see it's spreading out along here. And then the other thing the fact is you shouldn't be able to see the ray at all, as I mentioned before. The fact that you can see it means light is scattering and coming out from this page into your eyes. So you're losing light, and so that's why it's getting weaker and weaker. Now, as you can see from this diagram, I'm getting a second fainter line straight out of the machine, and so you can see it down here, it's on the bottom. And so I've gone back to the ray diagram to try and understand what could be happening there. So you can see from this ray diagram that what I'm getting is a dark line and then a faint one on top. And so I think I had it around this way at the time. And so for me, the only thing that would make sense to cancel out those weaker rays is if I put a line through here to cancel them out. And so what that must mean is the source inside my instrument must be slightly off center and down further than the slit. It's not exactly in the middle. And so I did some measurements, and fair enough, it's right. This one from the edge is about 46 to 47, 467 millimeters. And so when I go to this one, it sort of starts at 50. So it's a good 3 or 4 millimeters off, and so it does agree. And that explains why I'm getting a slight faint. If you have a careful look at it, most light boxes, if they're perfectly in line, they're going to have a faint line on either side. Okay? So the actual answer that they're really looking for is the incident light reflects a little bit off the top of the glass, and then it refracts down and then reflects properly off the silver. So most of it comes in this direction. Now, we haven't done angle of incidence equals angle of reflection. That's the next video, and the refractions are a little bit further on as well. There's even some geometry in there. And then I'll also, I'm not going to go over the sine, but we just use it, plug it into the calculator to get the exact angle. So we really need to do things to scale to understand how things are going on. So you can see this is too hard a question for our first experimental video. But anyway, I can see from this that the majority, the bright line will be the one furthest away, and the first one will be the faint line. And so that's the answer that they're looking for. And you can see that here in our experiment. You can see that the bright light has created a faint line here, although that artifact faint line would also be there. So it is slightly stronger than an incident light. So that's proving that it is reflecting off the mirror with both the strong light and the normal light. And then the main amount of light that's coming off is reflecting off the back of the mirror, which is this line here. So you can see the faint inner line right there. Okay, the only issue is there's a faint line on the other side. So when I'm in trouble, I get the laser out. The laser cuts down uncontrolled variables like just having monochromatic light, just one wavelength. Also, it being a lot stronger as well. And it's also much thinner. So it's just a better quality. So you're controlling the thickness as well. So you're controlling a lot of things. And you can see that this actually has the faint inner line, and then most of it's reflecting properly off the back of the mirror. So the faint inner line there reflecting off the glass, and then the proper refraction there. But it also has the third faintest, and the most faint is a little bit after it. And so once again, you have to go back to the ray diagrams. There's a line coming out here. And so there's a line coming out here. Right? And so the only thing that really would make sense is if a tiny, tiny amount of it is not actually refracting, and it's going straight through and then reflecting off. And so you can see the ray diagrams are essential. Otherwise, who knows what's going on. Okay, so hopefully you can persevere for all these videos, because there are dozens of them coming.